Question 2. Consider a hash table of size m where the keys are strings. For a string s of length n, s at I is the integer number associated with the character at index I. Rank the following hash functions from worst to best. So we're looking at these three here. And generally speaking, when you're looking at hash table functions, it's going to be the longest one that it's considered the best. It leads to the fewest collisions. Now, that is absolutely not the case all the time. I want to state that with stressed syllables, but generally that's what happens, because usually the function that has the most number of variables in it, the most number of factors that lead into determining what index the hash should be at, leads to the fewest number of collisions. So that's kind of what h sub 2 is doing. It's doing a whole bunch of stuff which leads to very different numbers, very different placements for what the key should go into after you run the hash function. So I'd kind of like to go in reverse here. So let's start with h sub 3 and see what it's doing. All it is doing is taking the size of the string, the key there, multiplying it by 17, and then doing a modulo of m. So that is pretty bad, because it's going to place every string that is the same length at the same index in the hash table. So for example, the string, what's two random words? Okay, we are at Purdue University. So gold and black, these are both 4 characters long. So based off of the function h sub 3, those are going to get placed at the same hash placement. So that's pretty bad, because that is a lot of collisions. Any two strings that are the same length are going to collide. So that isn't so good. So h sub 3 is going to be our worst one. I'm going to write that here. 1, 2, and 3 in bottom, and last place is h sub 3. All right, so what about the other two? Let's maybe look at h sub, actually that's pretty useful to keep around. Let's look at h sub 1. So what this is doing is this is a bit better now. It's factoring in each individual character of the string. It then multiplies it all by 17 and then modulates it. So this is a lot better than h sub 1, because it's not just relying on the length of the key, the length of the string. It's actually taking into account each individual character's integer value and adding them all together. So now gold and black will probably not lead to the same table placement anymore, unless they do by happenstance. And I didn't check. I just came up with that off the top of my head. But this still isn't quite the best, because what this means is any two anagrams that are the same length are going to have the same placement, and they're going to collide. So two words that are anagrams. What are two words that are anagrams? I don't know. Odd and Dodd. Sure, those are two anagrams, and they're the same length. So according to h sub 1, these are both going to be placed at the same, they're going to collide when you put them in the hash table. So that's also not too good, but it's certainly better than h sub 3. So we're probably going to put this in second place, h sub 1. Now let's look at, actually that's a crappy 1. That kind of looks like a 2. Let's do that. Can I write, please? There we go. All right. So now let's finally look at h sub 2. What is this doing? Well, it's kind of doing what h sub 1 did. It's taking into account each individual character's integer value, but it's multiplying each character by a different value. See, it starts off at 17 to the power of n minus 1, then 17 to the power of n minus 2, all the way down to 17 to the 0th power. So that's a lot better. Each individual character is not only accounted for, but it's being multiplied by a different value. So now most anagrams probably won't collide with each other. If we were to put in odd and Dodd into this, they probably wouldn't collide, unless they do by happenstance, but they probably don't unless you figure that out yourself. So because of that, this is definitely our best one, because it leads to the fewest number of collisions. So we are going to put that at the very top. h sub 2 is the best one, leading to our final ranking of the best being h sub 2, the middle being h sub 1, and the worst being h sub 3. Question 3. You're in the role of a hacker trying to break down a hash table. The information collected so far indicates the hash table uses quadratic probing, which is indicated by this. So for each probe that you do, First, you're going to have the key that you put in. So in this case, they're just integers. K is always going to be whatever you put into it. In this case, 16 and 35 and 10. And I is the probe's index. So the first probe you do, I is going to be 0. Then if it leads to a collision, the next probe is going to, I is going to be 1, and then 2, and so on and so forth. And then the modulus operator. So that's our hash function for the table. And its current capacity is it's 9 indices long. And this is the current state of the table. Looks like it's got a few values filled in, except for a couple, which will probably lead to some problems because collisions are no good. This system is nearly overloaded and will collapse if the next item inserted causes at least 4 probes. As an attacker, you are considering inserting the following keys, 16, 35, and 10. Which, if any, of these values would bring the system down if inserted? So let's go down the list. Let's start with key 16 and insert it into this, or at least try to insert it into this table using this function. So let's see what happens. I'm going to rewrite this first because that is all the way up there. hk, comma I equals k plus I squared modulo m. Cool. So let's start with 16. On the first pass, I guess the 0th pass, because I starts at 0, this is going to be 16 plus 0 squared modulus m. M is a size, which is 9. So this equals, let's see, 16 modulus 9 is 7. So that is 7. Index 7 is empty. So we are successfully, or I guess this is bad for us since we assume the role of the hacker, but we're going to insert 16 into index 7 because that was the output of the first of that probe. So key 16 did not bring down the table because there was only 1 probe in doing this. We need 4. So let's move on to the next one. What is the next one? 35. 35. On the 0th probe, this is going to be 35 plus 0 squared modulus 9. So let's see, 35 modulus 9, 35 minus 27 is 8. So let's see, is there a item at index 8? Yes, there is. 19 has already occupied that space. So we need to do another probe. Let's now do the first probe, or really the second probe. So now we're going to do 35 plus 1 squared, since with every future probe, I increases by 1, modulus 9. So let's see, 36 modulus 9 is a clean 0. 36 divided by 9 is a clean 4, so there's no remainder, so it's just 0. Is there something at index 0? Yes, there is. This may be looking good for us. We can maybe bring down this system. So index 0 is taken, so we have to do another probe. So the third probe, where I equals 2, this is 35 plus 2 squared modulus 9. Let's see, 35 plus 4 is 39, and 39 modulus 9 is 3. Is there something at index 3? No, there isn't. God damn it. 35 did not take down the table. So we're going to put 35 into index 3 and call ourselves failures, at least for now. So that sucks. But we've still got another key. Maybe this is the one. Maybe in key 10 will bring down the table. So let's see. At the first probe, where I equals 0, 10 plus 0 squared modulus 9 equals, let's see, 10 modulus 9 is 1. Is there a key at index 1? Yes, there is. So we're going to do another probe. So on the second probe, where I equals 1, this is 10 plus I squared modulus 9. So this is going to yield 11 modulus 9 is 2. Is there an index 2 filled already? Yes, there is. This is promising. We're already 2 probes in and haven't found a spot for it. We're shooting for 4. So let's see what happens next. This is the one. If this one fails, we will do another 4th probe, and we will successfully bring down the table. So let's see what happens here. 10 plus 2 squared modulus 9 equals, let's see, 10 plus 4 is 14. 14 modulus 9 is 5. Index 5 has an item in it already. Hallelujah. We have successfully nuked this entire table because we now have to do a 4th probe. which will bring down the table. That's what the problem said. After you do 4 probes. Wait, do they mean once you do the 4th probe, it brings on the table, or after you do the 4th probe? You know what? Let's just do this for the heck of it. Let's just see what happens. I'm pretty sure the answer is 10, and then this will also bring it down. But let's just see what happens. So 10 plus 3 squared modulus 9 equals, let's see, 19 modulus 9 is 1. And yeah, okay, it's still brought down the table. So there are definitely 4 probes here, at least. And the key of 10 successfully brought it down. Yay us. Question 4, merge sort. Yay. This is a very popular sorting algorithm because of how fast it is. It's n log n, which is, I don't know if it's proven to be as fast as sorting can get, but it is one of the fastest we know so far. Regardless, we are asked to perform merge sort on this string here, Hamilton. It's a convenient power of 2 length long. It's 8 characters, so that's nice for us since merge sort keeps splitting things in half. So it's nice for things to be powers of 2. So let's start off by writing out the whole thing. Hamilton. So how merge sort works is you keep splitting in half until you only have 1 character remaining. So let's first split it in half. On one side we now have HAMI, and on the other is LTON. Now I do it again for both. So on the left we have HA, on the right we have MI, and then we do the same over here. We now have LT and ON. Now I have to do this again. So this H and A are split, so now we have H and A, then we have M and I, then we have L and T, and finally O and N. So that's the first half of merge sort, just splitting it in half constantly until you just have individual characters remaining. And now the second half of merge sort is merging. So we are going to look at each individual pair that we've just split apart and see, and just compare them and sort them based on that. So which goes first, the H or the A? A comes first in the alphabet, so this now becomes AH. Now we do the same here. Between M and I, which comes first in the alphabet? I does, so that's I and M. Now we look at L and T. L comes first in the alphabet, so it's L, then M. And then finally, between O and N, L, M, N. N comes first, so in the alphabet. I had to say it out real quick because I forgot. Well, I need to go back to elementary school. All right, so that is 1 round of the second half of merge sort done. Now we just do it again. So we look between these 2 pairs and sort it accordingly. So how computers do this is it does kind of like a pointers system. So they both start at the first index, determines which is first, in this case A, so it writes it down here, and then moves it to the next, which is H, and then H is still the next, so it just puts H there, and then finally concludes with I and M. That is how it works, and you probably should know that, but all it's really doing is just, merging them into one sorted list. So now we have between L, M, and NO. This is already sorted, yeah, L, M, N, O. Yeah, so L, M, N, O is how you get that. And then finally, we have our last step. We have to merge these final 2 substrings. This is going to become, if we look at A and L, A comes first, so it's A. Then we move the pointer 1 over. H comes first, so we put H down and then move that pointer 1 over. I then comes first again, so write it down, move the pointer. Then L comes first, so we write down L, move L's pointer, so now it's at M. Then we write down, we've got 2 M's. Okay, it doesn't really matter what we do here, we just kind of write both. So 2 M's, 2 M's. This pointer, since it's now out of range of the substring, we just kind of flush out the rest of the other substrings. So now we just write N and O. And how did I get 2 M's? Wait, hang on a second. L, T. Okay, what the hell? Why did I replace this with an M? Okay, that's a T. That's still valid. This becomes, whoopsies. Okay, so That's N, O, T. There we go. Then we have here, it would just be N, O, T. Okay, that is how you sort this. That is how merge sort works if you know your alphabet and your letters, which I clearly don't. But yeah, this is how merge sort works. That's generally how you do it. I think we actually, maybe you guys do too, but we had a project about this. We actually had to implement merge sort ourselves using the pointers system. So that was pretty cool. So yeah, this is how merge sort works. Question 5. Let L be a list of n 10-digit numbers. Bruno proposes the following algorithm for sorting the n numbers. So let's kind of look at what it's doing here. That's really just a for loop. So for I from 0 to 10, it's just going to use selection sort to sort the numbers based on the ith digit. So that's what it does. And then a little disclaimer. So digit 9 is the unit, digit 8 is the tens unit, digit 7 is the hundreds unit, and so on. So for example, the 9th digit is 0, 8th digit is 6, and so on and so forth. What, if any, corrections are to be made so that Bruno's sort will actually work? If there are corrections to be made, explain why. So this function isn't quite correct because what it intends to do is sort it in increasing order. So basically, it wants to have the smallest number at the very start of the list and the biggest number at the end of it. But what Bruno's sort actually does is the opposite. It's going to stick the biggest number at the start of the list and the smallest number at the end after Bruno's sort runs. And the reason for that is this is basically just an inverted radix sort. So how radix sort works on a list of things to sort, in this case a list of n 10-digit numbers, is it starts at, for example, if I do some random numbers here like 3, 4, 9, 2, 8, I'll just keep it 5 digits for now. 3, 4, 9, 2, 8, and let's do 8, 9, 0, 3, 4. Cool, those are 2 numbers for sure. How radix sort works is it starts at the very end with the ones digit and then keeps moving down and sorting based off of the preceding digits. So for example, what we were to do here is we first look at 8 and 4. Okay, we can tell that 4 is smaller, so we are going to do a swap. We're going to put this bottom number at the top and then do it again. So we look at 3 and 2. Okay, 2 is smaller, so we're going to move it back to the top. And then it keeps going back and forth, swapping between up and down until you finally get to the final digit, in this case the 10,000s digit, and put the smallest one there. That's how radix sort normally works. But look at what Bruno's sort does. It is starting at the very first digit, because that's what they said here. Digit 0 is the, right? Did I set that up right? Yeah, digit, when I equals 0, it's going to be the very start of the number because when I is 9, that's the units digit. So it is starting with the biggest number and ending at the smallest, the ones digit. So this is going to sort it based off of the biggest digit first and then move forwards like this. And what this does is it does kind of sort the list, but it does so in decreasing order. So it's going to stick the biggest one up front. So that isn't quite what Bruno set out to do for his function, so unfortunately it is wrong. But fortunately, it's really easy for us to fix. We can just kind of modify the for loop a bit so that it loops from 9 to 0 instead of from 0 to 9. So we can just kind of make this a 10, make this a greater than sign, make this a 0, and then make it subtract at each turn instead of add. Boom, there we go. Now this works great. Actually, we would modify this a little bit. We'd make this a 9, and then make this a greater than or equal to, and then, okay, I think that's right now. But yeah, that's all we would have to do to modify this Bruno sort to make it just a regular old radix sort in order to make Bruno sort the list in increasing order. Question 6, part A. How many 2-3 trees exist storing the keys 1 through 5? So if we just kind of think about the structure first off, like just what the tree looks like, just the nodes instead of what's inside them. We really only have two options. The first one is we have a root with one value in it, and then its two children each have 2. So something looks like that. We'll worry about what the values are inside of them later. Or we have a root with 2 values inside of it with 3 children, each only having 1 value. So if we look like, we only really have these 2 different structures to look at, and if you try to construct anything else, it's going to violate one property of 2-3 trees. Like for example, if you try to do something where it starts with 1 value and then 2 children each with 1 value, well, we still have 2 more keys to fit into this. This one only has 3, but we still need 2 more. And there's no way to add more values onto it that will keep the tree balanced. Like we could do this where it each has 1, but then this one doesn't have any and now it's unbalanced. Or we could, revert back to what this is and have each child have 2 values. So this is really the only way this can happen. These 2 ways. We either have we have one of these, and that's the only way it can happen. And fortunately for us, each one of these 2 trees can only have one permutation of what values you put into it. So this one on the left here, it can only go 1, 2, 3, 4, 5, since when you kind of read it from left to right, it has to basically say out what the keys are in order. And on the right side, it's kind of the same deal. It goes 1, 2, 3, 4, 5. So that is how 2-3 trees work. These are the only 2-3 trees that work for this, because any other tree will either be unbalanced or it won't be sorted properly. So these are the only 2 that we can have. Part B, Bruno again says that the largest key in a 2-3 tree sometimes can be found in an interior node. Is Bruno right? So what interior nodes are is just any node that has children. So in this case, this node here and this node here are both interior nodes, and everything else are leaf nodes. Actually, I think nodes can be both interior nodes and leaf nodes if they are both derivatives of other interior nodes, or and they also have leaves coming off of it. But that's what interior nodes are. And yeah, Bruno's got to be wrong, because if we have any type of tree here, let's just do some copy paste. Let's just take this one. Actually, no, let's do this. I erased stuff. I continue erasing things. Why is this not going? Come on. Select. Thank you. Copy. Paste. There we go. So here, if we look at this tree here, the largest value is on the right here, which makes sense. That's kind of the definition of a 2-3 tree. It's always sorted like that, where the rightmost child, the rightmost leaf is the largest. And the interior node, which is up here, will always be smaller than the rightmost child of it. So, yeah, Bruno's wrong. The interior node does not have the largest node, the largest key in the tree. It's always on the right. Question 7. We're just building a big 2-3 tree. Are you ready? Let's do this. First off, we are going to insert 3. So we're just going to spawn the tree with a root of size 1. Cool. So now we're going to insert 7. Based off of 2-3 trees, a node can either have 1 or 2 keys in it. So we're just going to smush this 7 inside of that root there. That works. Now I need to insert 2. So unfortunately, this can't work where we just put the 2 on the left there and call it a day. Nodes can only have a maximum of 2 keys in it. So we can't just put the 2 there. So what we need to do is, if we were to imagine there were actually 3 keys in there, what we kind of do is pull the 3 up into a new root, and now both 2 and 7 are its children. So when we kind of do that, that leaves us with 3, and then on the left and right are 2 and 7. So that is how that goes. And now we need to insert 9. So how this is going to go is we start at 3. Okay, 9 is bigger than 3, so now we need to jump down to 7, and we put it next to the 7. So now this bottom node here is a 3 node with 7 and 9 keys. So there we go. Now we need to insert 0. So same kind of deal, except we're just going to go to the left. 0 is less than 3, so we're going to go to the left to 2. Now this is going to look like 0, 2. Remember, with each 3 node, we always, sort it because 0 is less than 2. It goes on the left. Now we need to, actually, let me double check my work, make sure it's right. Yes, it is. Okay, cool. Now we need to insert 11. So we're going to kind of do the same thing. 11 is bigger than 3, so we're going to jump down to the right and insert 11 into this node here. But we have a problem because this node now has 3 keys in it, which is no good. So we're going to kind of do what we did before. We're going to take that middle value, we're going to push it up, and then make make its left and right keys its children. So when we push 9 up, we're just going to kind of make that a neighbor of 3. So now this is a 2 node with 3 and 9, and its children are 7 and 11. Now we're going to make 2 children off of that because 3 nodes always need 3 children. So now this is going to be, 7 and 11, like this. So when we pushed that 9 up, we took that 9, which was surrounded by 7 and 11, and we made it have 2 children, which are the 7 and the 11, and we made the 3 and 9 cousins. So that's how that went. Now we need to insert 1. Let's see what happens when we do that. 1 is going to fall on the left. It's going to go down there. If we kind of imagine putting it inside of this node, we'll get 0, 1, and 2 as keys. That's no good because we can't have 3 keys in a node. So we're going to do what we just did. We're going to imagine pushing that 1 up to the top, up 1 layer, and then making 0 and 2 nodes of it. So when we do that, we're going to get, let's see here, I'm going to erase that. We're going to keep the 0 and 2 around, but make them separate nodes. So that goes there. This will be there. And now we have 0, 3, 9. So I guess it's a bit better, but it's still not good because we basically have a 4 node now. We have 1 node with 4 keys in it, and we also have 4 children coming off of it. So none of what I just said is appealing. So what we're going to do is we're going to introduce another layer. So we're going to do what we've been doing this whole time. We see that we have a node with 3 keys in it, and we're going to take that middle key and push it up. So that 3 is now going to go up. It's going to graduate into a new internal node up there, and its neighboring keys are going to be its children. So now we have 0 and 9 as standalone two nodes, I guess, and those are the children of 3. And now we're all balanced. Look at this. We have a balanced 2-3 tree. Everything is a 2 node because it has 2 children coming off of it, and it's completely balanced. Did I do something wrong here? Why is there a 0 here? That shouldn't be there. I think it's supposed to be... This is supposed to be a 1. Okay, never mind. That's supposed to be a 1. Everything I said was true, except that's just supposed to be a 1. So now we have a balanced 2-3 tree. Everything is jolly, but look what they threw at us. We now need to delete 3, which is the very root of everything that we've put here. So that's a problem. So let's see what happens when we try to erase it. This is now 2 different trees, which is not good. So let's kind of try to merge them. If we were to put this 1 and 9 together, this would give us 1, 9. This is now a 3 node, but it's not really a 3 node because it has 4 children coming off of it. So we kind of need to combine a few things. I think you can do this in 3 different ways. You can combine any 2 of these nodes into a 3 node. Are you supposed to do like the leftmost one or the middle one? I don't think it truly matters. I'm just going to do the left one because that's what I have in my solutions. I'm going to combine the 0 and the 2 into 1 3 node coming off of that, and now it's all balanced. This is a 3 node, and it has 3 children coming off of it, and all other nodes have no children. So everything is now balanced, and that is how you insert and delete stuff from a 2-3 tree. Okay, hang on. Quick amendum. This isn't totally balanced. What we need to do is swap the 2 and the 1. So that's a 1, that's a 2. And now it is balanced because when you read it from left to right, it's in order. 0, 1, 2, 7, 9, 11. So now this is the fully balanced 2-3 tree after doing all these operations. Final question. Show the steps to transform the array below into a max heap using the bottom-up approach. So just a quick recap of what heaps are. They're basically just array representations of trees. So what this array means, if we were to kind of convert it into a tree, it would look like this, where 5 is the root, and then we have 4 and 9 as its children. So, nope, not a 5. We want 4 and 9 as its children. And then going from there, we have 8, 10, 7, and 6 as all of its children. So we'd have 8, 10, 7, and 6. And finally, 3 coming off of the 8 there. So that's basically how we can transform an array into a tree and vice versa. And what a max heap is basically we want this, if you were to kind of do a level order traversal of it, we want every node to be greater than both of its children. So in this case, this is not a max heap yet, because if you look at this 5, it is not bigger than one of its children, which is 9. In something like if you look at the 9 here, it is in a max heap state since it's bigger than both 7 and 6, but the whole tree doesn't follow that pattern. So unfortunately, it isn't a max heap yet. So what we're going to do is we're going to apply a few different operations onto the array here. The specific way we're going to do this is bottom up, where we basically start at the bottom of the tree and then work our way upwards and do a few recursives of that until we're in a state where each node is bigger than both of its children. So let's start off by, I just erased it, but let's start by separating off the array into each of the levels that it'd be in a tree. So here we would have the root there, which is 5. Then we would have its 2 children on the second level, and then the 4 children on the third level. It's always a multiple of 2 like that. There's 1 root, 2 level 1 children, 4 level 3 children, then there'd be 8, and then 16, and so on and so forth. So we're going to separate it like that, just to make it a little bit clearer. And now I can go ahead and get started. So I'm going to rewrite all of this down below, and we'll just keep erasing and swapping values on it. So we've got 5, 4, 9, 8, 10, 7, 6, 3. And we are going to start, I think how we want to do this is we start basically, we start at the end. We start at the bottom, since this is bottom up. The bottom there is 3. Now, it doesn't have any children, so we don't have to check anything for it. But what is its parent? Its parent is always going to be, you take the index, you subtract 1, and then divide by 2. So in this case, 7 minus 1 is 6, and 6 divided by 2 is 3. So we're going to look at index 3, which is 8, and do a couple different checks on it. We're going to check if it is bigger than both of its children. So what we're going to do is I'm going to visualize this with an arrow. On the bottom there, we're going to see if 8 is bigger than both of its children. These would be 3, and usually there'd be another number after it, but 3 is the last child. So 8 only has 1 child, which is 3, and it is indeed bigger than that, so we don't have to swap anything. So after that, we're just going to go linearly down the line and do all those checks on 9, 4, and 5. So let's look at 9. Is 9 bigger than both of its children? So in order to find its children, we're going to look at its index. And how do you do this? I think you add, yeah, okay, cool. So we're going to add 1, and then multiply by 2, and then that and the one to the left of it is going to be its child. So 9 has an index of 2, and if we add 1, that's 3. Multiply by 2 is 6. So that is one of its children, as well as 5, the one right to the left of it. So 7 and 6 are its children. We're going to look at those. Is 9 bigger than 7? Yes. Is 9 bigger than 6? Also yes. We don't have to do any swaps yet. So now we're going to look at 4, and we're going to look at its children. Those are going to be, if we add 1 to 1, that's going to be 2. 2 times 2 is 4, and 4 minus 1 is 3. So 4's children are 8 and 10. So we're going to compare 4 to 8 and 10. Is 4 bigger than both of those? No, it isn't. 8 and 10 are both bigger than 4. So what we're going to do is we're going to swap out 4 with the bigger of its 2 children. In this case, it's 10. So we're going to swap 10 and 4 to make this. So that is how we do that. We've got one more step now. We've got to check 5 with its children. 5 has an index of 0, so we are going to add 1 to make 1. 1 times 2 is 2, and the one to the left of it is 1. So its children are the indices at 1 and 2, which in this case are 10 and 9 now. Is 5 bigger than both of them? No, it isn't. So we're going to swap 5 with the biggest of its two children, which is 10. So now we have 10 and 5. So cool. Are we in a state that is satisfiable? We don't know yet. We'd have to do another recurse to check that, since we just had a recurse where we had to do some swapping. You know you're done once you can kind of go all the way down the chain and you don't have to swap anything. So let's do this all again. We started at 8 last time, or at least the one at index 4. So we're going to do that again. We check 8 with 3. Yep, that's still good. Now we're going to check 9 with its children. That was 7 and 6. Is 9 still bigger than both of those? Yes, it is. So we're done with that. Now we're going to check 5. Is 5 bigger than its children, which was, which were they? It was 8 and 4. No, it isn't. It still isn't. So 5 isn't bigger than 8, so we're going to swap those two. So now this is going to be 8 and 5. So that's good. Now we're going to look at 10. Is 10 bigger than both 8 and 9? Yes, it is. So that's done. Now we just did a swap during that recurrence, so we need to do one more recurrence to see if we are all done here. So we always start with the same positions. Sometimes they're different numbers, but we always start with the same indexes. So we're going to look at 5, compare it with 3. 5 is definitely greater than 3, so we don't have to do anything there. Now we're going to look at 9. We're going to compare it with its children. 9 is still bigger than 7 and 6, so no swaps there. Is 8 bigger than its children, which is 5 and 4? Yes, it is. 8 is bigger than both of those. No swaps necessary. And finally, is 10 bigger than 8 and 9? Yes, it is. So now that we've done a full recurse, a full loop, without doing any swaps, we know that we're done. And now our finished array, which is this, is a complete max heap using the bottom-up approach.